Welcome to Fale, who's going to talk about Red Hat OpenShift on Z. And we are going to encourage asking questions through the chat. Then they'll probably be addressed at the end of the session, unless Fale decides otherwise. But feel free to put your questions in the chat at any time during the session. Right, Fale, I'll hand over to you.
Thanks, Jacob. So, as mentioned, we are going to talk about OpenShift, so containers on mainframes. And a little bit about me, I have been working in IT for the last 20-ish years, mostly in consulting roles, infrastructure side of the stack roles. I have also published a few books, and I am an EMEA principal specialist solution architect at Red Hat. So I tend to talk a lot about our technologies, both OpenShift, Ansible, and others. So let's start from the very beginning. And one of the key points about OpenShift itself is the idea of a container. Now, obviously, we are not talking about these kind of containers. We are talking about software containers. But the reason why software containers are called containers and not something else is because they have a lot of the same characteristics, the same ideas that are with physical containers. So an example of this is the fact that if we have a physical containers, we can do a lot of things with it. So for instance, we can put it on a lorry, we can put it on a train, we can put it on a ship, or we can have specialized infrastructure that is able to handle containers. And the reality is that we don't really care what is in the container as long as the container has those standard measurements, a reasonable weight, let's say, or a weight that does not passes the limits for the containers. Still, we don't really care what there is inside. There could be a car, there could be phones, there could be anything else. We don't care, because the important things for all those usages, if we are like transporting company or any kind of company that has to manage the container itself, is only about the externalities of the containers, which are very easy to identify and they tend to be standard. So this allows us to not really care too much about what there is into the container. Now, obviously, the person that put the thing in the container or will have to remove the content from the container will care about it. So in the same way, in the software world, we will have some people, such as the application developers, that will care a lot about what there is into the container. But the reality is that from an infrastructure standpoint, that is not important. So that makes us able to create a clear demarcation line between what is infrastructure and what is development. So in the infrastructure side, we only care about, is the container running? And then the developer is able to not really care about how his container will be used, because they know that whatever infrastructure we are going to provision them, it's going to be able to run their container. Now, there are a few concepts, a few advantages that containers bring us. Obviously, we have less overhead than running full VMs, because in theory, you can have a similar conversation with full VMs as well. So I am, from an infrastructure standpoint, I'm running VMs. Whatever there is in the VM, I don't really care, but the reality is that VMs are not that efficient to do this kind of thing. So you can do it with big systems, but it would make probably not much sense to have it for every single small package or software that you want to run. They have an increased portability because it does not really matter what there is in the container, as long as there are a few characteristics of the containers, as we will see, that are correct for the execution environment. And due to those aspects, it allows us to have more consistent operations. and also greater efficiency because we can better pack together applications in a smaller space. And this also will provide our developers a better application development experience because they will have a lot of tooling on their side as well to create containers or to test containers and those kind of things. So some use cases of containers are also lift and shift applications. So you have a classic application. Here we are talking about Linux containers, so it has to be a Linux application. If it's a CentOS application, that's a slightly different conversation. But if you already have a Linux application running, you can simply put it into a container and then start to be able to have all those advantages that we just mentioned. Another very common use case is the refactoring of an application into a container. So you might maybe have one big monolith, and then you start to chunk it out in multiple parts. And for every part, you put them into a container because obviously that will be easier to handle. But also, obviously, you can develop net new applications. And since you're starting with a new application, it might make more sense to develop it directly into a container lens space. Also, if you have microservices architectures, or if you want to reach microservices architectures, containers will provide you a lot more benefits because nowadays the huge majority of microservices applications are running into containers. So there is a lot of common knowledge on how to run microservices architecture already baked into container tooling and software. And also, one of the advantages of having a container is that it's always the same, and it means that it's way easier to actually put it into a CI/CD integrated in more complex CI/CD scenarios as well, and so on. And also, since the container itself it's easily replicatable, it makes it easier to deploy it multiple times or in multiple different situations. But OpenShift is not only about containers. It's also about something more, which is Kubernetes. Kubernetes is a layer on top of a container. And if we're talking about Kubernetes, there are some big advantages. First of all, it provides you service discovery and load balancing because the container itself is just containing your application. Now, this is already great, but it does not give you intrinsic value out of that containment. The only thing it gives you is that single size fits all API externally. And the way to leverage this is to use tooling. And Kubernetes is one of those tools. And one of the key aspects of Kubernetes is the fact that it gives you that service discovery, load balancing services that are very useful for the majority of applications. And since our applications are now in containers, containers are standard, it's way easier to create those kind of services in an abstracted way, where then every single application works properly with those services. There is also an aspect about storage and storage orchestration. Even though some applications are stateless, obviously that's great. The reality is that the huge majority of applications actually have storage and storage requirements. So effectively, Kubernetes also takes care of a standard approach to storage to those standard applications in containers. And also, it helps you automate all the rollouts, rollbacks, and all those kind of operations that are simply place containers, remove containers kind of approach. And due to this, it's also doing some bin packing optimizations that you can leverage thanks to that standard shape of containers. Also, due to the fact that it handles those containers, it can do self-healing applications. So, for instance, let's say that your application needs to have at least two running replicas. If Kubernetes finds out you only have one, for instance, for whatever reasons, a node died, an application died, whatever happened, Kubernetes can respawn your missing application. And also it does manage for you, or can manage for you if you want, secrets and configuration, so that all your application can easily read and potentially write those secrets and configuration that are then available to the containers that you choose within your environment. A couple of things on Kubernetes naming, because as everything in IT, it tends to be an abstraction layer and create new kind of terms for things that you might be used to naming in different ways. So first of all, we have the containers. As before, we discussed about the aspect of the container, but the interesting thing about the containers, I think, is that in reality, they are not really anything too fancy. If you are aware of how Unix system works, they have a tree of processes basically, and what you can do is take a branch of this tree and say, from this point onward, all those processes will be tagged with a certain tag. And what a container is exactly that. It simply creates a new branch where your application will run into, and it will tag that branch and all the child processes in a certain way, and then apply certain constraints to the tags, basically. And this allows you to limit access to system resources, to other applications, or be limited or limit other application to access your system, your processes. There is the concept of a container image, because a container, the way it starts, it starts from a container image. And a container image is basically a target set of your application and all the required dependencies, which means that as long as that container is standard, that container can run on every single version of Linux and potentially also different distributions and so on. And because all the dependencies are there. And also, this means that once you have tested that container image to be okay, so your application works with the dependencies that are within the container image, then it will always run, as long as obviously the container image does not change. There is in Kubernetes the concept of a pod, which is basically a group of containers that have to behave in a certain way, so they have to collaborate basically. So they will be co-located, for instance, on the same host. And then the concept of service. So service is a higher level abstraction layer from an application standpoint. So what you can have is maybe have multiple pods, because you have maybe multiple replicas of the same container, and you want to have them on different machines. But in reality, from your application user standpoint, they don't really care which of the replicas they are hitting, as long as they have a running replica that replies to their query. So effectively, they can call the pod, which is a networking item, and that pod will then load balance between the various, call the service, and that service will load balance between the various pods that you have. Also, there is the persistent volume. Here is going back to that point about the storage and the fact that Kubernetes is going to provide you the storage primitives to be able to create stateful applications. Config maps is the way Kubernetes handles configurations, and secrets is the way Kubernetes handles secrets that we discussed. So there are a few Kubernetes components. Basically, there is a decentralized storage database in the center of Kubernetes. There is an API server, which is a control plane API that simply queries the etcd database and potentially modify its state. A control plane node is simply any node that executes an API server and a TCD. A worker node, in the other hand, is any node that execute applications that the user cares about. Infrastructure nodes are then other kind of nodes that simply do provision other services that are required to run your applications, but are not your applications and are not the API server. So hybrid cloud and multi-clouds is the new normal. There are a few stats, but 89% of IT leaders says that they are already running on multiple clouds. Those can be either public clouds, private clouds, mix of the two. And this is going up. 87% it was last year, so this is increasing. 90% of the people say that they want to run the application where it runs best. This can be on-prem, on edge, on cloud, and anything else. And also, there is an expectation that still 43% of the workloads will be on-prem. And the 65% of buyers prioritize software, or better, things as a service. Those can be software or other kind of things, as long as they are as a service, basically. And I think out of those points, we can reach a conclusion, which is there are a lot of applications that are going to clouds. Very few people will go only in one cloud. It will tend to be on multiple clouds, multiple architecture. And I think this is a critical aspect, because I think there is a huge space for the Z architecture to also have, as we'll see later, a space into this situation. The way OpenShift works is that it's an abstraction layer. And this, I think, is the critical aspect that can help ZED to be part of that big multi-architecture hybrid cloud environment. Because since OpenShift and Kubernetes more generally, but obviously we're talking about OpenShift, is an abstraction layer for whatever there is below it, it might be very convenient in certain cases to run it on specialized hardware such as that. And the components of OpenShift are obviously Kubernetes, that's the blue strip into the graph, but also many other components that will give you that full experience that the simple Kubernetes is not able to provide. There are a few installation options available for OpenShift on ZED. You have the single node installation option, which basically means you get one single node and you just install OpenShift on it. Now, obviously, that means that you do not have any high availability or those kind of things. If you want to do an update, it will disrupt all your services. So this is not a production grade kind of installation, but it's great if you just want to test a few things, develop, or have a playground environment to start to see exactly how everything works. It will require very few IFLs, so it's a very easy way to start. There is then the 3 nodes cluster, where basically you create 3 different systems, and then you have HA and all the other fancy things, let's say, about OpenShift, but you still have not a huge amount of IFLs, and you have limited scalability. So if you want to scale up your cluster, that would be a little bit more tricky. And then there is the production grade kind of installation where you have at least 5 nodes, 3 data controller nodes, and 2 compute nodes or worker nodes. And then you can eventually increase the number of computer nodes distinctive from controller nodes, which means that if you want to onboard multiple applications over time, you can add more and more computer nodes so that basically you have enough resources for all of those. Now, obviously, you can also increase the size of your nodes, giving it more IFLs, for instance, or more RAM. But that obviously it's not always the best choice because you have to then have you have bigger loads to schedule and so on. But that's also a possibility also. There is also a very interesting aspect that I think that has been developed in the last few years, and I think it's the most interesting one probably, way of installing it, which is the multi-architecture. So back in 4.14, it was possible to create a multi-architecture deployment. So basically some nodes on x86 and some on Z system. But the way you would do it is you would have the control plane on x86, and then eventually you could add some compute nodes, S390 X compute nodes to that cluster, which was okay because you can start to use the application running on S390, but still you do have a disadvantage that if the control plane goes down, so if the x86 machine goes down, then you would have a situation where basically your application would not be able to restart itself, for instance. So in 4.15, they solved this. And from 4.15 onward, we do have additional features where basically you can do the opposite, where basically you can provision a cluster on S390 and then only after that add some nodes that are x86 for certain kind of applications. And also, after version 4.15, we got new versions. 4.16, for instance, added the agents installer parity for multi-architecture systems or multi-payload installations, where basically this means that you have multiple options to install a multi-architecture cluster. And then in 4.17, we also added the hosted control planes of x86, where basically you have the hosted control plane on x86, and then you manage full clusters on Power Z. And then in 4.18, we also have the addition of the multi-architecture tuning operator. So that basically it's an operator, an OpenShift operator that is help you to tune all the to tweak basically all the options in the various platforms to ensure the maximum performance. So as you can see, there is a lot of investment into this kind of multi-architecture approach, and this is going to be very important if you want to have those situations where easily you can move application from one architecture to the other. Now, there is this idea that I really like, and the idea is to have a Linux One system as a management hub. So the idea is to have a cluster, an OpenShift cluster on S390, and then put on top of it some multi-architecture, multi-cloud management tools. There is, for instance, Red Hat Advanced Cluster Management for Kubernetes, which basically is an abstraction layer on top of Kubernetes that allows you to manage multiple Kubernetes or OpenShift clusters throughout your estate. And if you put it on Linux One, also you will have all the advantages of uptime and so on that Linux One guarantees you to ensure that your single pane of glass is always on. And the other advantage is that obviously you would have this on-prem and then potentially manage clusters that are not on-prem. But also you can manage every kind of Kubernetes installation, not only OpenShift. So you might have, for instance, EKS, that is the managed Kubernetes on AWS, and you can still manage it from this kind of architecture, but also multi-cloud and multi-architecture. And another aspect is to put all the automation, so for instance, OpenShift pipelines that are across multiple OpenShift clusters or other kind of Kubernetes clusters around, and still have all the pipelines running or be managed, better say, on this management hub. So effectively, this means that you are splitting the management side from the execution side. Now, the execution side might be on x86, it might be on S390, might be on any other platform, or on-prem, in cloud, wherever, but still that management side, I think it would be better placed on an S390 kind of architecture. So the big question after all of this, since we have spoken about a lot about the fact that this simplifies to migrate things, is does it still make sense to run this on S390? Or is this a risk more than other things? And I think the reality, and I've come to this conclusion after a few years of conversation about this, is that containers will not displace the mainframe. They will simply enhance it by running on it and by bringing new workloads to the mainframe as well. So why Red Hat OpenShift on the mainframe? First of all, there is a point about development consistency. A lot of developers really like to have that containers tools that they are used to, and they don't want to sacrifice it to develop for Z. But if they can use the same tooling on Z, then why not? Also, there are a huge amount of companies, tools, projects, everything around containers, because containers is basically a standard that has been created, a contract between parties. So it's very easy to create a product around containers. And by having the ability to run containers on Z, we also get the ability of using a lot of those in tools that are very convenient. And also the workload portability part. Now, workload portability is not complete in the sense that obviously, if you have S390, x86, and other architectures, you will, and if you have a binary application, you will need to rebuild it for every single architecture you will want to run it on. Because, I mean, you could potentially run it in some kind of virtualized way where there is transcoding between the various architecture instructions, but that would not be efficient. So you want to recompile it every time. But the reality is that the code from where you create those images would be the same. So that could be helpful to the portability part. And the other big question is, if everything we said is, makes sense, why using OpenShift, or better, using running OpenShift on the mainframe and not somewhere else? And I think there are very valid reasons. One is data gravity. So every time you have to query data from a different system, obviously it will cost you time. If you can co-run the application with your data, then obviously you will get better performances. And in a lot of cases, data are on mainframe. So obviously it would make sense to have applications running there as well. And there is a big aspect in mainframe space about low latency between helpers, which is not something you would have on x86. Consolidation and TCO are great points. Even though a single mainframe will surely cost more than one single x86 box, the power it gives you is completely different. There is then a point about business continuity, because you will want to have all applications running at all the times. Now, though OpenShift and Kubernetes help with resiliency, the reality is that they help with certain kind of resiliency, not with all kind of resiliency. And also, mainframes have unique hardware capabilities, such as the security cards that really have performances that are not possible to reach on software stacks, because of the hardware is always faster than software. And going back to the business continuity point, there is an important aspect that it's very important to focus on, which is how it works HIA NDR. So OpenShift only handles pod failures, not node failures. And this is not an OpenShift problem, it is how software is designed, how Kubernetes is designed. So if your pod goes down, Kubernetes or OpenShift can pick it up and run it again. But if a node goes down, Kubernetes does not know what to do, because they don't manage the nodes, they just use the nodes. So they will see a reduction of available resources. OpenShift also needs a majority of etcd running. So by default, you would have 3 etcds, which means that at least 2 of the 3 etcds needs to be running. If that condition is not met, then it will go in read-only mode, basically, and will stop acting on your application, which means that if you lose, for instance, 2 etcds and a bunch of pods, OpenShift will not be able to restart those pods. And also, the whole OpenShift Kubernetes is software defined, which means that a lot of times, if it's associated with software defined storage as well, RTO0 or RPO0 are not things that can be done. Those are known limits of those kind of architectures. They do have a lot of advantages, but they do have limits as well. So the mainframe HA capability can, I think, solve all those 3 major issues that an architecture based on Kubernetes has, because obviously you would have RPO0, RTO0 that can be done. But also at the same time, if some iPod go down, you can have the mainframe systems, restarting it or ensuring that it never goes down in the first place. So that effectively, that guarantees you to have always nodes available, always all the etcd up and running, and the storage with RPO0, RTO0, and then from there you can leverage Kubernetes to also ensure that all your applications on top of that are properly running. So there is also an interesting aspect, which also is that you can pick and choose which kind of HA you want to have. You don't have to run every single application with the same level of HA and DR, because obviously that would be costly. But you can pick and choose to ensure that you always are running at the correct level with the correct insurances around HA and DR based on the specific workload that you are talking about. So wrapping up a little bit, there is a key a key point about focusing on portable applications, because containers can make your application more portable. That does not mean fully portable, as we have seen, but more portable for sure. Containers can bring new tooling to mainframes, all those tooling that are container specific can come to the mainframe if you're using containers there as well. At the same time, mainframes are great platforms to run containers because they provide that additional HA, DR, and guarantees that are very important, but also the data gravity part, the high performance, very specialized hardware, and so on. And OpenShift enables portable application without giving up all those characteristics that are very typical of the mainframe and the reason why so many applications need to run on mainframes. So with this, thank you all. There is a feedback form available. Please complete the feedback form. And I'm not sure if there are questions in the chat or people have questions to write on the chat.
Yeah, let us know if you have any questions. If you have a question and you'd rather ask it in person, let me know and I can unmute you. You can talk to Fala directly. Well, while you think about questions, I was just wondering, Fala, actually, you talked about the multi-architecture approach where you can have your workloads and your control nodes, for that matter, distributed across different platforms. Yep. Does that include containers in Z as well? So rather than containers in Linux on Z, using ZCX from Z, I think it's called ZCP maybe these days.
Yeah, so at the moment, that is not the case. But it could be that over time, that will become the case because the reality is we have started to see those multi-architecture installations being possible. I would say beginning of 2024, so 1.5 ish years ago, and over the course of the last year and a half, we have seen a lot of new features coming in. So I would not be surprised if in maybe 1 year time we'll be discussing about this again. But the reality will be that also non-standard Linux containers will be available for the orchestration in this way.
We'll look forward to your presentation on that next year.
Yeah.
Also, if we don't have any other questions at the moment, I was just wondering if there are any particular types of workloads that you think are really well suited for this, or any types that maybe don't work so well with containerization and Kubernetes at the moment. If you had any comments on that.
Yeah, so I would say let's start from the last part. So what does not really work too well, and what does not work too well is the cases where you need to have exactly n version n instances of an application running. So if you need to have exactly one version or exactly one instance or three instances of an application running, that's a little bit complex on Kubernetes because Kubernetes will always try to get to the proper number, but it might be in some cases plus minus one. But obviously over time, that's eventual consistency basically. So over time, it will reach to the correct number. If your application really requires to have a specific number of instances, then obviously Kubernetes might not be the best solution for you. In the other hand, what works well, basically everything else. You do not get any performance hit by using Kubernetes. You don't get any weird stuff. It's simply an application running with certain tags and managed by Kubernetes that has those behavior of automatic healing and restarting your services when needed. But also your application needs to be able to handle being restarted or not running in exact number of replicas.
Okay, thank you very much. Last chance if anyone else has any questions. And also, do remember to submit feedback. It's very easy. There's a direct link from the agenda to give your feedback. So please do it. Okay, if there are no other questions, I'm going to close the session. Thanks very much, Vale, for presenting, and thanks to everyone who attended. And our next session in the hybrid cloud stream is tomorrow at the same time, so tomorrow at 12:30, which I will be chairing as well. So hopefully I'll see some of you there. And that will be Daniel will be presenting there. He's with us just now. Okay, thanks very much.
Thank you, everyone.